Testing, testing. Okay, this is lecture 11. It's the second part of the study of geometry, launching off from chapter 11 of Boas and Geller. What I'd like to do today is just to discuss a quantity called curvature, and in order to do that, let's just go down to this brief little summary for arc length and curvature formulas that I've created, just out of a text file. So as soon as that loads, let's bump this up a little bit. Okay, so you'll remember, and this is going to be a little review of multivariable calculus here. If you have a curve in 3 dimensions, and what I mean by that is, I'll draw a picture. If you have a curve in 3 dimensions, so here's your cube, which is R3, 3 dimensions. We have a curve in 3 dimensions, can be parameterized by any point x, y, and z as x of t, y of t, and z of t. Now, if the curve is straight, like a line, we'll find very shortly that it has no curvature. But if you have in a plane, which this is a 3-dimensional, if a line is bent, the deviation of the curve away from the tangent line has to do with the curvature. So if you put a circle tangent to this point right here, let's move that circle in, the radius of the curve at that point is related to what we call the curvature. Now obviously if the curve is very curved, like this, the circle inside here is going to be very small. So the curvature is going to essentially be like 1 over the radius. So we're going to think of a quantity called curvature. It's going to be like 1 over the radius. Now in 3 dimensions, it's a little bit harder to develop this concept, but you have the idea of a tangent to the curve at a point. You have a normal to the curve, and then these two determine a plane, and you have a binormal, and so you have a little 3-dimensional coordinate system moving along every point of this curve. And if we know the representation of this, or r of t, this 3-dimensional vector, through derivatives we can calculate the tangent, the normal, and then the binormal, and that's what these formulas are here. So the unit tangent, if we have r as a function f, g, h, or x, y, and z of t, the tangent to the curve is r prime, and if you divide the tangent by its length, absolute value, it's equal to the unit tangent. Now if you integrate this tangent as a function of t, you'll get the length of the curve between a and b. And the arc length as a function is just letting the upper limit be variable, t. It goes from a to t r prime. Now, notice the derivative ds dt is positive, so s is a monotonically or monotone increasing function, and that means it defines a invertible function s of t, so you can find s as a function of t and invert that to find t as a function of s. Now, if you do that implicitly, where t is a function of s, the curvature is defined as the rate of change of the normal with respect to arc length. Now, getting t as an explicit function of s is quite hard. You have to actually compute an integral and then invert it. But if you use the chain rule, instead of dt by ds, dt by dt little t and s by t, you have the curvature parametrically is the ratio of the derivative of the tangent, unit tangent, divided by the derivative of the arc length. Now there's also a unit normal, since the derivative of the tangent's orthogonal to the normal is orthogonal to t, so it's normal direction. And the unit normal is t prime over t. And then they define a third normal. This determines a plane, and then the normal to the plane is called the binormal. So this is a way of getting parametrically the quantity, the ideas of a tangent, a normal, and then the binormal. So we have this little system of coordinates that moves along with it. Now, in 3 dimensions, or as a surface, we have to extend this a little bit. And so let's see what we do in terms of a surface. So how would you define the length of a curve on a surface? Well, if you have a surface in 3 dimensions, that means you can parameterize the surface, if it's a regular surface, by 2 parameters. And what you're doing is essentially, if you have a surface in 3 dimensions, you're writing a local coordinate system, say u here and v here. So this is your surface S, and you've got some x as a function of u and v, y as a function of u and v, and z as a function of u and v. So think of this as being surface coordinates, and if you have a sphere of fixed r, then you can have a polar angle phi, and you can have a angle theta, and the point on the sphere is completely determined by longitude and latitude, the theta and the phi. Now in 3 dimensions you need the r, but if you're on a surface of the sphere, r is fixed, so you can determine x as a function of theta and phi, etc. So that's how we do it in general. We have 2 coordinates, u and v, and the 3-dimensional coordinates x, y, and z are parameterized in terms of u and v. Now if you parameterize x, y, and z in terms of u and v, the length of the curve will be determined by this differential here. Namely, the arc length squared will be dx partial x partial u squared du squared plus the inner product of x dx du dx dv du dv, and then dv squared times dx dv length squared. Okay, so this is called, in differential geometry, the first fundamental form. And in terms of E, F, and G, you can define what is called an intrinsic curvature. That means it's a curvature that's defined only by quantities within the surface itself, as there's a very complicated formula. Now it turns out that that doesn't depend on how you embed this surface in 3 dimensions, so you don't need x, y, and z coordinates, you just need these coordinates here. So the point of this is that as soon as you define what this metric, this way of measuring length on a surface, you essentially can calculate the local curvature of that surface. And actually it's a very nice problem in mathematics to specify the curvature at every point and then try to find a surface, integrate that to find a surface with prescribed curvature. So there's a very nice problem, and that is, given this curvature at every point, at every point in space, or every point on the surface, construct the surface. Now, this Gaussian curvature has a nice property that if you have a plane, the curvature is 0. If you're on a sphere, the curvature is positive and constant. You can also have curvature negative. And where you have those are in the so-called hyperbolic spaces, which are like saddle point surfaces. So if you measure the arc length along here, you'll end up with a form that gives rise to negative curvature. And so it's an interesting question now that was debated very hotly is according to the physics and the laws of physics that we have, is our space positively curved, is it flat, or is it negatively curved? So this idea of curvature gives an idea of how area distorts locally and how. Now there's a very nice reference here. Let me go to that, jumping around a little bit. And that is, how would an ant measure curvature? Suppose you're a being that lives on two-dimensional space, embedded in three-dimensional space. And there's a nice little article here on how an ant on a surface embedded in R3, how they would find whether their space was flat, positively curved, or negatively curved. Now this link here, it tells how a being that lives to the surface can measure the Gaussian curvature at a point. So the idea is, imagine that you're an ant and you're living on the surface, and you're tied to a point P with a fixed length R. So the ant runs around P in a circle while the thread is completely stretched, and you measure the circumference of one complete trip around P. So if the surface were flat, okay, so here you are at P, you have a length R, and you go around in a circle, you make one complete orbit, and if you're a flat surface, then obviously the circumference is 2 pi r. So if the circumference is not 2 pi r, that means your space is not flat. And depending on whether it's bigger or smaller will tell you whether it's positively or negatively curved. Now here's the formula. On a curved surface, you can define the Gaussian curvature at a point P by taking the limit as the circles get very small of the flat space result, 2 pi r, minus the circumference that you actually compute, and divide by pi r cubed multiplied by 3. Now what this says is if the circumference C is smaller than 2 pi r, K is bigger than 0. So that means the curvature is positive. And this means if it's bigger, curvature is negative. Now let's see why that might be. Suppose you're on a part of a sphere. Suppose you're on the top of a sphere. Like so. And you have a piece of string that has length r, so along the surface is r, and you traipse around the surface like this. And you calculate the distance, the circumference, as a function of r. Now, if you can see what's happening here a little bit if you took the same point and had a fixed r and this length S is equal to r, and look at here, you would calculate 2 pi r. But if your surface is positively curved, what happens is this is bent along the surface in such a way so that this circle, if you project it down, this circle would actually lie inside the circle here. So that length in the tangential direction, if you calculate the length that way, it's kind of deformed. You could think of this as suppose you're living even on the top of a mountain like this. And you have this little rope that goes down here, and then you move it around your universe, and you get a tiny little circle, right? Versus if you were flat around a circle like this. So if you have very large positive curvature, this circle that you calculate the distance of along your space is much less than the distance you would get, assuming you know what pi is, assuming that if you had that absolute number pi, assuming that you can calculate this, you can compare it to that and determine, in this case, your circumference is much less than the flat space result, so your space is positively curved. Now, if you're in a saddle point space or a hyperbolic space, and suppose you're living in a space that looks like, oh, I misdrew it. So we go like this. If you're here, and you draw a line segment up here, you can see what happens is it'll go along in here, and then it'll kind of flatten out, and then it'll go up, and then it'll go down, etc., like this. So imagine you lived in a space which is kind of fluted. And I don't know how to even draw that, but imagine that your little line segment here going down in your space traces out a path that is highly oscillatory like this. So supposing your path, and these were points on your surface, and this is kind of like a scallop shell. If you move along your surface, it could inscribe a very long path. And in this case, the circumference might be much bigger than 2 pi r. And in that case, the surface would have negative curvature at this point because it's associated with this kind of wavy in and out. It's not something that looks like a top of a sphere. It's something that looks like a scallop shell or a saddle. Okay, so in fact, there is a way for the ant to tell what the properties, the local properties of curvature for the world that he lives on, even though he can't leave that space in 3 dimensions and measure things. He can't take a picture of it. Now it's very interesting here, if you go back to this, radial space, if you lived on this universe, you would very quickly discover that as you made your R, let's go, suppose you literally lived on a sphere like this, and that's all your world would know. And suppose if you're up here and you have a little short string, you move around in a little circle, and you make the string a little bit longer, and it moves around. There will come a point where your string reaches halfway across, and the circle is as big as it gets. But then when you make the R even bigger, you end up getting a little circle again. So if you were on this universe here, as a function of R, your circles would be small, larger, larger. They would reach some maximum, and then they would basically shrink again. So this universe has no boundaries, it's positively curved, has no boundaries, and it is finite. Now also notice that if you have a line, the idea of straight line segments here are just these great circles, these geodesics. So if you want to calculate the distance, shortest distance between 2 points, you look at the geodesic that contains them, and the distance between any points is the straight line, quote unquote, along this geodesic. This picture here, and if you view this as a straight line, and this is a point not on the straight line, and you draw a line through here, there is actually, it will intersect the geodesic on the opposite side. So in other words, if this, let's draw this again. Okay, and so here's one of your great circles, and this, it goes through the origin. So you take this point in the center, put a plane through it, and where it intersects, it defines this great circle. But now you have a plane off of here, a point that's off of here. Well, it turns out you could have a geodesic that basically would intersect here and would intersect at this point. So what this would say is you could draw a line segment that's off of here that would intersect at these points. In fact, infinitely many of them. So you'd have lots and lots of parallel lines here. So the properties, the local properties of a surface determine the local curvature. And the properties in the large, like boundary, and this is geometry, and the properties in the large, like does the space have holes in it, is it shaped like a donut, etc., is a subject of topology. So topology is properties in the large, global properties, and the geometry is local properties. So it's very interesting in our case, in 3D and physics, can we deduce local curvature of our 3 space, and can we deduce global properties of our universe? Is it closed in on itself? Does it look like an infinite sphere topologically? Is it negatively curved? Is it shaped like a saddle? Does it have a boundary? If you go out infinitely far, do you come in a circle and come back again? So these are questions that physicists strive to answer, sort of like our ant. They'll take measurements. In fact, Euler himself, it's very interesting, he was, no, I believe it was Gauss, when he was surveying, he made the observation that if you were a being that lived on a circle, it is no longer true that the angles of a triangle, so alpha, beta, and gamma, we know in flat space, this has to add up to pi, which is 180 degrees. But on a circle, in a sphere, it doesn't do that. So take something on the North Pole and make it a quarter of a circle around here so that this is 90 degrees. So just when you're looking down at the top, it's just a 90-degree angle. Now look at the equator, where these intersect is 90 degrees. This is 90 degrees. And if you add up all these angles, you have a triangle with 3 90-degree angles. So if you're on the surface measuring this little angle, you'd say, oh, that's 90 degrees, this is 90 degrees, and this is 90 degrees. And so this is what Gauss did, actually, while he was surveying. He went very far away and took line of sight, he took surveying instruments, and he went very, very far away, and he said, okay, let me calculate the angles and see if they really do add up to 180. Because up here, when you're very flat, the triangles get very close to 180 degrees. But as you make these triangles larger, the sum of the angles can actually be bigger than 180, in this case 270 degrees, this wedge-shaped quarter of a wedge. So as your dimensions get larger, is it true that the sum of the angles actually equals 180 degrees if the triangle is large? Now, if you lived in perfectly flat space, that would be true. But if you lived in a curved space, as we actually do, it would be possible if you could get a big enough triangle, because remember, the sun, for example, distorts the space in the neighborhood. If the sun's down here, the geodesics are no longer straight. So if you did a triangle between 3 points in space, these are no longer straight lines. In fact, they might look sort of pinched like this. And so this angle in here is actually less than the flat space angle. This little cusp is less than this, and this little cusp is less than this. So the sum of the angles would be less than pi. So if we lived in a curved space, as we do, and we went very, very far out and made a triangle that was, say, the size of the Earth to the Moon to Mars, then you could actually determine that the angles would be slightly less than pi. Now, Gauss could not move out to Mars or Jupiter or stuff, so he just did surveying on miles or so, and he could not detect any difference in the sum of the angles in a triangle for as far as he could go out, which is pretty clear. Okay, so let's go back to the first link, which is the history of curvature. The idea of curvature actually goes back to Aristotle. And this is a very nice summary here. So the geometry history goes from the ancient Greeks, which we've studied, to Fermat and Descartes in the era of analytic geometry in the 1700s, and finally differential geometry. And then there was the algebraic analytic geometry inside there. So curvature has been a constant thread through each of them. So if you look down here, it gives a quote from Aristotle in Proclus's History of Geometry that there were 3 kinds of loci: curves, straight curves, circular, and mixed. Apollonius, which dealt with solid geometry, has the idea of conic sections and normal lines. And for about 1,500 years, nothing really much happened until the 14th century when this fellow, Nicole Oresme, this is an interesting quote, he has generally been determined to be the first person to draw a graph. I don't know how they would determine that, but I guess he's the one with the earliest manuscript that has a graph in it. And he seems to also be the first person to hint at a definition of curvature. So he actually assumed something which he called in Latin curvitas, which was equivalent to a measure of twist. And then they actually had this idea of fitting a circle tangent to a curve, and the smaller the circle, the more curvy it was, and that's essentially fitting an oscillating circle to a curve. And finally, when it became possible to describe geometry in terms of coordinates and algebraic curves and things like that, in other words, Fermat and Descartes, they were able to describe general curves with algebraic equations, algebraic geometry. Now, when calculus was invented, then they were able to look at derivatives and define what's called differential geometry, and define curvature in terms of derivatives. This goes down through Newton and all the way down. The last link is Carl Friedrich Gauss. And he was essentially put the geometry, differential geometry on the map. So curvature is one of these threads that goes from early Greek days all the way to Gauss. I found a nice little introduction to curvature of surfaces. Again, these are a lot of words and very little mathematics. And this makes the point that if you take a flat piece of paper and bend it without crinkling it, only one direction at a time, you can still calculate triangles and you can still calculate straight lines on the surface. And you can still calculate, for example, that the angles will add up. Since you're not deforming the intersection, you're not locally stretching the surface, the angles along the cylinder will still add up to 180 degrees. But if you start really deforming and stretching, that means that it's locally your curvature is locally a function of your position. You can get very interesting things. So again, take a look at that link. I found a very nice course on, it appears to be an undergraduate course on differential geometry, and he's broken this up into a bunch of PDF files, and one of the ones in here discusses a formula for the Gaussian curvature, which is equivalent to, let's see if I can make this a little bit bigger. So he discusses a formula here for Gaussian curvature, which is equivalent to the formula that I gave in the case where f is 0, so it's equal to this. And f equals 0 just means that you have orthogonal coordinate system on your surface. So you can go down through there. There's numerous references in here, starting off from very simple curves, curvature in the plane, to arc length, to the Frenet relationships, calculating curvature and torsion in a 2D curve in 3 space, and surfaces, tangent planes, etc. So that's a bunch of PDF files. If you haven't had a course in differential geometry, that would be a very nice introduction to it. As I mentioned before, there's a very deep interaction between modern physics, theory of general relativity, and the local curvature of space. This PDF manuscript is 40 pages long and it has some nice pictures in it, but this is more or less a nice little slideshow. Now this is from Australia, so it does talk about coordinates relative to Melbourne, Canberra, and Sydney. So it says, supposing you are in a flat one-dimensional space, it talks about how you would measure distance. And you would measure distance by line segments. Now if you were in curved one-dimensional space, you could still integrate the arc length around there to determine the distance. But the geodesics, which are curves along this plane, are no longer straight. This is a space which is one-dimensional and has constant curvature. And if you were a worm living inside this circle, knowing no other two-dimensional or three-dimensional world, you would say that this was a closed universe. That is, it has no edge, it's finite and unbounded. Bounded means there's no boundary, no edge. Now, we can look down from 3 dimensions and see all this, but we can't look on our 3-dimensional world from 4 or 5 dimensions. We don't have that capability. Now, if you're in 2 dimensions, and you're in flat space, Pythagorean theorem, which is just using a metric with coefficients 1 and constant, so the curvature is 0. And this discussed that as a function of scale, the Earth is locally flat, but it really is curved. It has a great deal of distortion near mountains and things like that. So you can walk your way through this, and it goes on to discuss the surface of a sphere, great circles, which calculate geodesics, and on. So I won't go through all that, but it's a very nice presentation on leading up to, in 3 dimensions, the curvature of space. There's a nice theorem that I found a relationship to, Gauss's theorem, between circumscribed polygons and the computation of total curvature. And so this theorem states in the plane that if you have a polygon with n sides enclosing an area A, then the sum of the interior angles minus n minus 2 pi is equal to the total curvature of A. So you could actually calculate the total curvature of a curve by means of circumscribed polygons. So that's one way you could calculate this, practically speaking. This is a nice reference to the various forms of curvature and how you would calculate it. Now, in general, there are 2 different types of curvature. There's what's called intrinsic curvature, like Gauss curvature, which means that it doesn't depend on how you embed your surface or curve in space. The calculation of the curvature is a property of that object, that set itself, and not the maps that embed it into space. In other words, if you parameterize the surface with parameters u and v that amount to coordinates in the plane, in the surface, then the Gauss curvature is an intrinsic invariant curvature for that surface. The extrinsic curvature, which were these Fresnel formulas, are not invariant. It depends on how you actually describe the curve in terms of 3 space. Now this has, every one of these is a link. So there's mean curvature, Gaussian curvature, average curvature, Ricci curvature, sectional curvatures, which is the same as Gauss curvature, etc. You can go through a link on all of these. Now this goes through what I did on the PDF file of defining curvature as the rate of change of the normal with respect to arc length, because that's what you get all the way down here somewhere. We have passed it. Somewhere in there. And these are the famous Frenet formulas, which are parametric descriptions of curvature and arc length. Now, the Gaussian curvature is relatively complicated to compute, but it's the same formula as what I got in the PDF file. And what leads to the Gauss curvature is this differential form here called the first fundamental form that tells you in your coordinate system how to calculate arc length in terms of u and v. Now this is a rather complicated formula, and this is the one that I've essentially reproduced in the PDF, but it is invariant. It doesn't depend on how you embed the surface. And in practice, it's computable just within the surface itself. So in practice, we could compute our local curvature of space by use of that. Now we've already talked about how an ant would measure the curvature. There's a link here on, again, metrics and curvature of space. And this talks about the parallel postulate and the link to Euclid's 5th postulate and the existence of other kinds of spaces. Now these are example of metrics. The normal Pythagorean theorem metric, Euclidean metric, just says that your distance in 2-dimensional flat space is this delta x squared plus delta y squared. Now if you change the units, for example, you do it in centimeters and feet, you might get a slightly scaled metric. If you do it in polar coordinates, you would have a factor r squared in there. On the other hand, and if that's fixed, so if you change variables, you can transfer one metric into another, but sometimes, like going from a sphere to a plane, you can't do that because there's this variable coefficient in here that you can't deform. And this is what they call the taxicab metric, or L1 metric. It's just the distance between 2 points is the distance along one street and then into the next street. So that's kind of funny. The taxi cab metric is you calculate, it's like you're going on a street. To go from here to here, you have to go up a street and then over. And so that's the distance. And that induces a metric on the space. Now, there's a nice discussion here on Einstein's equations, because Einstein wrote down an extremely nice equation. I'll just put it in here. This is see if I can find a better formulation of it. Because the Einstein equations essentially predicted black holes and other things that were just discovered shortly after 1917. I found a really nice reference to, it's called a map to space-time in Einstein in navigation. So it's just a visual front end to here. But if you go down here and talk about here's Einstein field equations, this is Einstein's famous field equation in here, where G is just a tensor with indices, and this T is a tensor. G relates to gravitation and mass, and this relates to forces. So this is an equation that relates the gravitational field. Given a mass, you can calculate the gravitational field and the warping of the space around it, and then obviously the space determines how light rays and things travel and also how forces are propagated. So it's highly coupled. If you distribute masses in 3 dimensions, the distribution of masses will curve the space, and the curved space will then affect the distribution of masses. So in 1916, he published this paper, and in 1903 or 4, I think, was a special relativity paper. So 13 years later, he did this, and a fellow by the name of Schwarzschild was the first to apply his theory. And this is a really interesting story. He was basically a German scientist. He was stationed on the Russian front, and in his spare time, I guess in between battles, he read Einstein's paper and actually looked and found a radially symmetric solution of it, which led to a singularity, which is now known as a black hole. So Schwarzschild died, just, I don't know, a year, weeks, something, a few months later. So Schwarzschild died a few months later after he sent this paper to Einstein, and then Einstein presented the paper in his memory at a conference in later that year. So, but he describes a singularity, which is a pointwise region of infinite curvature. And Einstein read about this and called it the Schwarzschild singularity, and came up with this idea of a black hole. Now, the black holes, interestingly, were actually thought of 200 years earlier. Back in the 1700s, Laplace actually considered the possibility of a star so massive that the gravitation would be so strong that light could not escape it. And that's essentially what we understand as a black hole. Okay, so the Einstein equations, which relate curvature and through these differential geometrical ideas, they are a very extremely complicated set of equations, and they have only been able to be solved numerically. Some of the problems that come from geometry are actually some of the most interesting problems that you could think of, because they have to do with our understanding of the universe that we live in. Namely, can we tell if we live in a flat space or a curved space? Well, it's sort of like the ant. You could do local measurements very, very precisely and see whether triangles, for example, do they add up to 180 or are they sort of pinched? Okay, so the sum of the angles would be less than pi. Or are they kind of on a sphere, are they bigger than this? So whether they're pinched in or pinched out, this is the curvature that is negative, and this is curvature which is positive. So this is spherical geometry, and this would be hyperbolic geometry. Can we tell that in our three-dimensional space? And if the space is curved, is it positively curved, negatively curved? And I didn't put this down there, but question number 3 was what's the global properties of our space? Does it have a boundary, or does it not have a boundary? Is it finite? Is it infinite? And this sort of ties into with the Big Bang, although that adds a measurement of time into it. I should also mention that these, let's see, I don't know if this is the one here, but if you put in a metric that, is not positive definite, so in other words, this is the Minkowski metric of special relativity, you'll see that it's the speed of light times time occurs with a plus here, and the space-times come with a negative. So that leads to an E and an F and a G that have different properties, and this, I believe, leads to a hyperbolic geometric view. Okay, I'm going to cut it off here. I will mention that the homework is for this. I'll just remind you, the homework is due for the limits on Tuesday of next week. And be sure to, if you have any questions, ask me, email or otherwise, about the limits. I'll be posting sometime soon another homework number 5 on some geometry. And we'll actually give you some of these things and let you calculate distances on a donut, things like that. So I will also be posting, for some of you, particularly the distance students that have not done limits in a while, I'll go through a couple epsilon delta proofs and some of the finite infinite series, and I'll put them on the web as a streaming video file. So there will be, under the section on videos, after the lecture 11, Geometry Part 2, there will be a brief little video on epsilon delta limits so that you can review how to construct the deltas given epsilons, etc. Okay, again, apologize for